So welcome back to the aerodynamics class. In the last class, we had a discussion on the symmetrical airfoil, and we have calculated the coefficient of lift and lift curve slope and so on. And we will continue the discussion today, right? I acknowledge John T. Anderson's Fundamentals of Aerodynamics. So this is what we have done in the last class, where we want to say that the camber line is a streamline for the chord, right? So we have started with this discussion, and then we have arrived to a conclusion by calculating the coefficient of lift, that is L dash by Q infinity S, and then we have arrived to CL is equal to 2 pi gamma, 2 pi alpha, where dCl by d alpha is equal to 2 pi. So we had a conclusion that the CL versus alpha curve, if you draw by even experimental calculation for a symmetrical airfoil, it looks like this, and the slope maintains 2 pi, right? So now we will have a discussion on the moment, right? Because the force and the moment coefficients are the important characteristics of any airfoil. So we need to calculate the moment now, right? So before calculating the moment, I would like to visit our symmetrical airfoil discussion once again in order to have some understanding, right? So let me draw a symmetrical airfoil, right? So this is a symmetrical airfoil, and we have a leading edge here and a trailing edge here, right? So when there is a free stream velocity V infinity, because of the shear force and the pressure force, right? Here you have a pressure force, and pressure acts normal to the surface and the shear force here. So shear force acts tangentially on the surface. So because of that, you have a distribution of force, right? Something like the distribution of forces around the airfoil, right? So one can draw a distribution of force, right? Now there is a question where you will place the resultant of this force, right? Where you will place a resultant of force at any point in the chord. Okay, if it is so, where you will place, right? So one can talk about the resultant of the symmetrical airfoil, right? So we can say that there is a point called center of pressure. Okay, so I will write this as N dash as a normal force and A dash as an axial force, and the location of this point I mark this as XCP, that is from the leading edge, right? So always in our cases, the moment is acting like this, and the moment acts at a leading edge, I consider. Moment acts as a leading edge, right? So the center of pressure is a point lies here, right? I say this center of pressure, the point at which the center of pressure, so the center of pressure is the point at which the resultant of the distributed load effectively acts on the body. So how the forces are produced? Because of the shear force and the pressure force. The resultant of the pressure force and shear force acts at a particular point. That point is called as the center of pressure, right? So now if I do some calculation, say moment about the leading edge, so that I can write as minus x Cp into n dash. So one can calculate the x Cp, that is equal to minus m moment about the leading edge by n dash, right? So now we have a question, how to take the moment, at what point, moment about the leading edge, moment about the center of the card, or moment about the quarter point of the card, or taking moment at the center of pressure, right? So if the moments were taken about the center of pressure, the integrated effect of the distributed load should be zero, right? Say I will draw that situation. Say we have a symmetrical airfoil, and let me take, say, considering the L dash here and the drag force here, and taking the moment here, that is moment about the leading edge. So the resultant force now lies in the leading edge. Okay. So there is a second case, and I take it here, say L dash, D dash, and I take the moment as here, moment about the leading edge. So this location, I consider this location as the C by 4, that is at the quarter card point. Now I take another case where somewhere you have a center of pressure, L dash, and here you have a D dash, and this distance is xc, as we have drawn before. Now here I didn't mark the moment, right, at the point at which the center of pressure lies, right? So if the moment were taken about the center of pressure, then the integrated effect of the distributed load should be zero. So in other way, the alternate definition for center of pressure is the point at which the aerodynamic moment is zero. The aerodynamic moment is zero, right? So when there is a small angle of attack, let us say the angle of attack is very small, then one can write sine alpha is almost equal to 0 and cos alpha, right? Sine alpha is almost equal to 0 and cos alpha can be equated to 1. If that is the case, you have L dash is equal to N dash, right? So we can write this N dash as L dash. So that doesn't matter. So one can write x Cp can be equated to moment about the leading edge by L dash, right? So now think about it. What happens if the lift reduces? If the lift decreases, the xCp increases. What is xCp? the distance from the leading edge to the resultant. So now let us consider if the lift becomes 0, a case, right? Then the center of pressure moves to infinity, right? Then XCP moves to infinity, right? So it is not a good idea always to consider the center of pressure for all our discussion in aerodynamics. Hence, it is necessary to formulate another definition which can suit for various purposes, right? So, say, let us go with this, right? We have already the expression here. We have the center of pressure location, right, and the moment, right. So in this case, the resultant is placed as the leading edge, and here the resultant is placed at the quarter cut point, and here the resultant is almost at the center of pressure, right. So one can write the moment about the leading edge. Say I write the moment about the leading edge. Say by considering this figure, I can say L dash minus C by 4 into L dash, right? So plus the moment about the quarter cut point, because this resultant I am keeping at this point, but the center of pressure may lie somewhere. So once I want to calculate the moment about the leading edge, I can calculate L dash multiplied by this C by 4 and the moment about the quarter cut point. So that can be equated to minus X Cp into L dash, right? So one can write this equation, right? So the moment about the leading edge can be expressed by C by 4 into L dash plus moment about the quarter cut point. Let us keep this aside and let us move back to the calculation of moment for the symmetrical airfoil using thin airfoil theory, right? So let us continue our discussion for the moment, right? Say we have calculated already the coefficient of lift, that is 2 pi alpha, and the dCl by d alpha is equal to 2 pi, right? Now let me write here, say this is a leading edge, and I draw this as a chord line, right? And I would like to show an elemental zeta, right? Say this is a elemental zeta d zeta, and the location of this zeta we can, this is from the previous discussion, right? So here I have a L dash or the elemental lift dl, right? And for the whole, one can take the d gamma is equal to minus gamma of zeta into d zeta. That we already know, right? We have all this information, right? So I have just drawn this particular one. Now let us calculate the total moment about the leading edge per unit span. So let me write m dash. Let me write the elemental moment is equal to minus zeta multiplied by dl. dl is a elemental lift that we know. The dl multiplied by this zeta. So now for the total moment, let me write the total moment. So total moment about the leading edge, right? So leading edge per unit span. So the total moment about the leading edge per unit span due to the entire vortex sheet. Due to entire vortex sheet. So we can write the moment about the leading edge per unit span due to the entire vortex sheet can be written as minus integral 0 to c zeta into dl. So we already know the expression for the zeta dl and all. So let us write L is equal to rho v gamma, right? So minus rho infinity v infinity integral 0 to c, instead of gamma d gamma I write zeta gamma of zeta into d zeta, right? So this is our equation, right? Now we need to transform this equation, right, and calculate moment about the leading edge. So let us start. So the moment about the leading edge, right, that is equal to minus rho infinity v infinity integral 0 to c zeta, then gamma of zeta into d zeta. And we already know what is zeta and what is gamma of zeta when we want to transform it in terms of theta. So let me write that minus rho infinity v infinity. When I convert that into theta, then I write 0 to pi and c by 2 into 1 minus cos theta into gamma of theta into d theta becomes c by 2 sin theta d theta. Right? Because we already know what is zeta, because in the last discussion we have made that zeta is equal to c by 2 into 1 minus cos theta. Right? Now, this can be reduced, right? This equation can be reduced. So let us reduce this equation. Minus rho infinity v infinity into, because we already know what is gamma of theta is equal to 2 alpha v infinity 1 plus cos theta by sin theta. So we can write rho infinity v infinity. I will write directly c. We have c by 2 c by 2 c square by 4 and 2 alpha v infinity integral 0 to pi 1 minus cos square theta, because we have 1 minus cos square theta, 1 plus cos theta, and all those. Finally, we can write 1 minus cos square theta into d theta. Right? So, by reducing this, we can write finally minus rho infinity v infinity square c square by 2 alpha and pi by 2. So we already know rho v square into rho v square by 2, that is equal to q infinity, and c square pi alpha by 2. That is the moment about the leading edge. So moment about the leading edge is equal to minus q infinity c square pi alpha by 2. What is q infinity? It is a dynamic pressure that is calculated by half rho v square by 2. So now we have arrived to the expression of moment, right? So we can calculate the coefficient of moment. Let us say coefficient of moment about the leading edge, that is equal to, I hope you remember why I use the small letter M, C and all those, because it is for the airfoil, not for the wing. So moment about the leading edge by q infinity S into C. This is what our definition for moment coefficient. So we know in our case S is equal to the chord into 1, because per unit span. So we can write the coefficient of moment about the leading edge. Coefficient of moment about the leading edge is equal to moment about the leading edge by q infinity c square, because S is equal to c into 1, and hence we can write this is equal to pi alpha by 2, because the moment is equal to moment about the leading edge can be written as minus q infinity c square pi alpha by 2. So q infinity c square and q infinity c square gets cancelled, and we can write minus pi alpha by 2. Now we will have a small discussion here. So if I write, say, from the previous equation, we know CL is equal to 2 pi alpha. So pi alpha is equal to CL by 2, right? So let us replace this pi alpha by CL by 2. So coefficient of moment about the leading edge can be written as CL minus CL by 4. Coefficient of moment about the leading edge is equal to minus CL by 4. Right? Now, let us take the moment as we have discussed here, the moment about the quarter chord point. Moment about quarter chord point. So the moment about the quarter chord point can be, so we have an equation here, right? So here you have a moment about the quarter cut point. So one can write moment about the quarter cut point is equal to the coefficient of moment about the leading edge plus CL by 4. Right? When you have this equation, we can write. So I will write the same equation, coefficient of moment about the quarter cut point is equal to coefficient of moment about the leading edge plus CL by 4. So what we infer here is coefficient of moment about the leading edge is minus CL by 4. So when it becomes minus CL by 4, we can write that the coefficient of moment at the quarter cut point is 0. Right? So the center of pressure, right? The center of pressure is the point about which the aerodynamic moments are 0. Right? The another definition we have given sometimes back. So for symmetrical airfoil, the center of pressure is at the quarter cut point. Right? So this is what we find. Right? Again, the definition for the aerodynamic center, right? So we will have a definition for aerodynamic center, right? The point on the airfoil airfoil where the moments are independent of angle of attack, where the moments are independent of angle of attack. Dependent of angle of attack is called aerodynamic center. But in the case of the center of pressure, where the all resultant force acts and also the aerodynamic moment is 0, right? So in the case of symmetrical airfoil, both aerodynamic center and center of pressure are same, right? At least theoretically we can say both are same, right? So let us have a discussion. Let us summarize the thin airfoil theory, right? So to start with, the thin airfoil theory is to find a distribution of vortex sheet strength along the chord line that will make the camber line a streamline of the flow, which satisfies the Kutta condition of gamma of trailing edge is equal to 0, right? So we have obtained the vortex distribution, right? And then we have gamma of zeta, then gamma of zeta converted, transformed into gamma of theta, right? And we have arrived to various results. So the results are, one is CL, that is equal to 2 pi alpha. And the next point is the lift slope. The lift slope is dCl by d alpha is equal to 2 pi. And then we have arrived to a conclusion on moments that the center of pressure and the aerodynamic center are located at the quarter chord point for the symmetrical airfoil, and both are same, right? Both are located at the quarter chord point. That's all the inference of the thin airfoil theory. Today we have discussed about the moment, then center of pressure, aerodynamic center, and its significance to the symmetrical airfoil, right? So I stop at this point for the today's discussion. Right? Thank you.